We now move on to the last section in topic 7, which is section 6, which covers the sigma and the pi bond. Alright, so let's do a little review of what we just learned in the last section with hybridization. So when you're dealing with hybridization, particularly for a situation where there are multiple bonds, a double bond or a triple bond, the hybridization process is still the same. So if we were to take a look at this particular molecule that we have here on the screen, ethene, and we were to take a look at our two central atoms, which are the carbon atoms here, I would still ask myself the same question. So I would say, all right, what's the number of electron domains around this first carbon? And so we would check and say, okay, we got 1, 2, 3 electron domains. Recall that the double bond only counts as 1. So if we have 3 electron domains, that means that this is going to be hybrid orbitals of sp2. And if I were to ask myself the same thing for the other carbon atom, right? Okay, 3 electron domains around that carbon atom, and so that would also need sp2 hybrid orbitals. So let's review what that looks like, right? So if we think about carbon and think about its electron configuration and orbital diagram, so we have 1s2, 2s2, and then we have 2p2. Right, so we actually don't really care about the 1s because that's not valence, so I'm just going to get rid of that just to make it a little cleaner. Right, so we've got there's that s orbital, and then remember we've got the p orbitals, there are 3. Okay, so it's going to look something like this. There are 2 electrons there, and then here's your 2 electrons there. Alright, so that's what the orbital diagram would be, and so we've already actually figured out that we need an sp2 orbital, right? So to make this bonding happen with this first carbon right here, we know that it needs the sp2 hybrid orbital. So when we do our hybridization, when we do our promotion, right, we know that this electron is going to move itself right here. Okay, so I'm going to put that electron there, and I'm going to see if I can get rid of that one electron. There we go. So that's what we end up having after the electron gets promoted, but we only need the s and then these 2 p orbitals right here to mix to end up getting our 3 identical orbitals that are these are the sp2 hybrid orbitals that we need, right? So these 3 electrons here, here, and here in these identical hybrid orbitals is what bond to this hydrogen, that hydrogen, and then that carbon. And obviously, since, this is carbon over here on the right, it's going to have the same situation. It will go through the same hybridization. It'll get these 3 hybrid orbitals to bond to this hydrogen, and then that carbon. Great. But we still have this leftover p orbital right here that never actually mixed, right? It never got hybridized. It was just the s and then these 2 p orbitals that mixed to create what we have down here, which is the hybrid orbitals. So what happens with this leftover p orbital, right? And I'm going to draw that in actually. Remember the p orbitals kind of look like that dumbbell. So this carbon has this p-shaped orbital that is singly occupied. And obviously this carbon has this, this carbon has the same thing, right? So it also has a p orbital that's singly occupied. What goes on there? Well, what actually ends up happening is these p orbitals will overlap. And when they overlap, they create a new bond. And so if we were to take a look at a much cleaner view, so we have our 2 carbon atoms here. Okay, we have carbon and carbon. So we see that those 3 hybrid orbitals are here, here, and here for that carbon. And then here, here, and here for the second carbon. And they're going to overlap with the hydrogens as well as with each other. That's great. That's what ends up creating this right here. So if we were to take a look at our molecule again, that's what ends up creating this. But then you also have, and I'll do it in a different color, I'll do it in blue, you have these p orbitals that we showed that are going to end up overlapping. And it actually, that's shown right here. That is what actually creates these, what we would call the second line of our double bond. And so this is where we're going to get our 2 bonds we're going to look at in this section, which are the sigma bonds, which have the Greek symbol for sigma. So that is for sigma, and then also the pi bond. Okay, so let's review what we just learned. We just learned that bonds that are made using the hybrid orbitals are going to be called your sigma bonds, and bonds that are made using the remaining p orbitals are going to be your pi bonds. So when you're taking a look at a molecule, how can you quickly tell what are sigma and what are pi? Well, every single bond, no pun intended, every single bond is going to be sigma. All right, and I'll write that off to the side here. So single bonds are always going to be sigma. And then also, when you're looking at a double bond or a triple bond, the first line is also, and that's kind of heavy, so let's see if we can make that a little bit smaller. Okay, the first line here is also going to be sigma. So I'll put single bonds are sigma. First line in a multiple bond is also going to be sigma. And then any additional bond, and I'll do this in green, so for example right here, those are going to be your pi bonds. And so additional lines in multiple bond, that's going to be your pi. So as another example, if I were to show you this molecule here and ask you to identify how many sigma bonds and how many pi bonds are in this molecule. So first of all, sigma. Here's a sigma bond, here's a sigma bond, and then the first line is sigma bond. And arbitrarily, I'm just choosing this bottom one. It doesn't matter, it's any of those. But there are 3 sigma bonds. And then how many pi bonds do you see? That would be any additional lines that you see. So it would be those 2. And so there would be 2 pi bonds. And you can see that down below, we actually show that. So these hybrid orbitals, well, let me make that a little bit thicker. Okay, so these hybrid orbitals here that overlap, that's what creates the sigma bond between the 2 carbons as well as the carbon and hydrogen. But then these p orbitals overlap to create this 1 pi bond. But then also this other, let me do purple, this other p orbital here and here overlap to create another pi bond. So that's where your 2 pi bonds come into play. So let's look at an example of how this might be phrased in an example question. So in example 6, I give you the structural formula for 2 compounds, and I'm asking you to identify how many sigma bonds and how many pi bonds are there. If you want to try it on your own, which I suggest, pause the video now and count, and then hit play to reveal the answers. Alright, so first I'm going to count my sigma bonds. And so sigma, remember, is going to be any single bond. So 1, 2, 3, 4, 5, and 6, 7, 8, 9. But then in anything that's a double or triple bond, it's the first line. So 10, 11, and 12. So there are 12 sigma bonds. That's the Greek symbol sigma. And then if I were to count how many pi bonds there are, let me get a green color here. That's going to be that additional line there, 1, 2, and 3. So there are 3 pi bonds. And then if I were to go over to the second structure here, so let's count my single bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15, and 16, because I also have to count how many lines there are in the double bonds. So there are 16 sigma bonds. Obviously, I'm not really good at drawing the sigma symbol. There we go. And then if I were to count how many pi bonds there are 1, 2, 3, and then 4. 4 pi bonds. Obviously, you can see that it's not a hard concept, but it leaves a lot of room to potentially get it wrong just because you got to make sure you count all of them. So definitely take your time and make sure that you catch them all. But that's how you can identify how many sigma bonds and pi bonds there are in a particular molecule. Well, that wraps up section 6 as well as topic 7. So we'll see you in the next topic.